Batteries provide the power for billions of mobile and embedded devices. The physical characteristics of batteries influence how we design both hardware and software.
Batteries have a number of physical characteristics that can affect overall system design. What combination of characteristics is best depends upon the application. We have nominal voltage and current, total energy, energy density, shelf life, how long we can leave the battery before it goes bad, the number of charging cycles before it stops taking a charge, internal resistance, performance versus temperature, and a number of other characteristics. We can use a number of different battery chemistries to build batteries. Alkaline and nickel-cadmium or NiCad are commonly used in smaller consumer electronic devices. Lithium-ion is used in smartphones and other applications that require high power. We can see that these chemistries vary quite a bit in various characteristics: their nominal voltage, their capacity, and the number of cycles we can charge and discharge them over. Specific energy is one very important characteristic. Specific energy is the energy per unit weight. This table compares the specific energy of several different types of materials. And we can see that a lithium battery has about 40% of the energy density of TNT. The lithium-ion battery that we find in so many devices has an energy density of about 15% that of TNT. So the energy density of these types of batteries approaches that of explosives. And remember that an explosion is an uncontrolled and fast release of energy. So when we deal with such high energy densities, we should be ready for the possibility that the battery, if it goes out of control, may have a violent reaction.
The discharge rate of batteries helps us determine when the battery is about to run out of power.
This is a typical voltage versus time curve for a battery we might find in a cell phone or a consumer electronics device. Earlier in the discharge cycle, the voltage is pretty flat. It may vary a small amount, drooping slightly, but it will be pretty consistent. As we start to run out of charge, the voltage drops very quickly. And we can in fact use this to indicate that the battery will run out of power soon. If we can determine that, we can then start to shut down the system in an orderly manner and avoid losing data. The smart battery system is a standard that's used to connect batteries. The smart battery system is a standard for adding circuits that provide information about the battery that can be queried by the host system. The system management bus for the smart battery system is based on the I2C standard, which is a very common serial bus. The system can query the smart battery system in order to find out the current state of the battery and other characteristics. Things like battery voltage, current, and temperature. The smart battery charger manages charging.
Discharge characteristics also have some surprising implications for system design.
Here's a cross-section of a battery with electrolyte sandwiched in between the anode and the cathode. The graph on the bottom shows the concentration of species, which is the molecules in the electrolyte that carry energy that can be extracted, as a function of position. So this graph shows how many species containing energy are at each position along the length of the battery. If the battery is fully charged and we're not drawing any current, then we have a high concentration of species uniformly across the battery. As we start to draw current, we will deplete species more heavily at the cathode end because electrons travel from the anode to the cathode. So the current is extracting more electrons from the part of the electrolyte that's closest to the cathode. If we let this process continue by running the battery, eventually we'll deplete all of the species at the cathode. The battery will stop producing current, and the system it's connected to will probably crash. This happens even though there are other species at the other end of the battery that still have energy, but they're not at the cathode, so we can't sustain a current. Puchardt's law captures this effect. It says that the capacity of a battery depends upon the discharge rate. The faster we discharge, the less capacity the battery has. So this suggests a strategy for battery management to extend the life or capacity of the battery. If we run it and then let it rest, the species will diffuse naturally across the battery. They'll tend to even out their concentrations. So now if we run the battery again, we have more species at the cathode end and we will have more capacity. And regularly letting the battery rest will give us the best capacity for the battery.
To review, batteries have a number of important physical characteristics: the amount of charge they hold, the number of times they can be recharged, and so forth. Energy density is a critical characteristic. On the one hand, high energy density gives us a compact battery. On the other hand, the energy density of modern batteries approaches that of explosives. Puchardt's law tells us that a battery's lifetime becomes shorter as its discharge rate increases.